Hi, welcome back to the shop. Today I want to talk about these induction heaters that you can now get on eBay for relatively cheap. They're about 7.2 kilowatts, peak 15 kilowatts, and they turn 240 volts electricity coming out of the wall into really efficient heat that takes no hydrocarbons, makes very little noise, and it's pretty portable, as I'll show you. So the basis for this technology is called induction, hence the name. And you've probably heard about it before from like induction stovetops or things like that. So the only thing you have to know is something called the right-hand rule. And this is one of many in physics where if you have a current traveling along a conductor in the direction of my right-hand thumb, the magnetic field will be generated in the direction of my right-hand fingers. So you'll have basically this spiral of current, of a magnetic field going around a conductor that's carrying current. So if you take a conductor and you wrap it into a coil, what you get is the sum of those magnetic field lines as the current is going through this coil. You will get basically a toroid or a donut shape that wraps around this coil. And so you'll get a concentration of magnetic field lines inside the coil. The most field lines will be towards the edges of the coil, and you get a relatively small number of field lines going through the very center of the coil. So this will come in handy when we talk about coil design. The converse of the right-hand rule also applies. So if you put a piece of metal through this coil and you have the magnetic field lines going this way along the direction of my right-hand thumb, it's going to generate a current in the direction of my right-hand fingers. And so everywhere a magnetic field line pierces this material along its length, you're going to generate a small eddy current. And the thing about those eddy currents is if you sum all the vectors, basically what you get is a current in the material going in the opposite direction of the current in the coil. So if the current in the coil is going this way, the current in the material will be going this way. It's sort of the material resisting through its own inductance the current that's trying to be applied to it through the coil, if that makes sense. So in an induction heater, this process, the direction of the current, actually switches tens of thousands of times per second. And that's important for some reasons that I won't really get into. But basically, this induction heater is rated to run between 30 and 80 kilohertz, which is about ideal for surface heating of metals. So the direction of the current will first be going this way, and then it'll be going the other way. So it'll be going this way, and the direction of the magnetic field will follow. So the current in the material will also be switching direction tens of thousands of times per second. This isn't really important for the heating of the material. The bulk result is that the current in the material heats it. So there is a difference between different types of metals when it comes to induction heating. If I take a piece of copper and put it through the coil, it'll heat through eddy currents, just like I told you. Eddy current heating is actually relatively slow, and you'll notice that if you put an aluminum pan or a copper pan on your induction stovetop, it won't heat that efficiently, whereas a steel pan or a cast iron pan will. And the reason is that when you have something that's ferromagnetic, like iron or steel, it actually generates heat through another mode. So when we're talking about ferromagnetic materials like iron, steel, nickel, and cobalt, they all have this property where the small electron orbitals inside the material can align themselves or be aligned when a strong magnetic field is applied. And you can think of this basically as little arrows inside the material, and when you apply a very, very strong magnetic field, some of those arrows all stick in the same direction. You can remove the magnet, and the object actually has a little bit of magnetic properties. You can probably notice this in your shop around screwdrivers. They always pick up metal chips and things like that. So when we have the magnetic field generated by the induction heater, right, we're generating a magnetic field this way and this way, tens of thousands of times per second. And so the electron orbitals inside the material align themselves with the magnetic field tens of thousands of times per second. And when they switch, this process isn't perfect. So the molecules sort of need to vibrate a little bit and flip their magnetic polarity. In doing this, it creates some losses. And those losses end up as vibration between the molecules, which is heat. So long story short, forcing the molecular orbitals to switch direction with the magnetic field generates a second heating mode, which is why ferromagnetic materials heat so much faster with induction. So if you remember before, when I told you that the field lines are most concentrated near the surface of the coil and less concentrated at the center of the coil, it's obvious that we're going to have more of a induction heating effect at the surface of the metal. And so this will happen at the surface. If you look down the end of a long bar as you heat it, you'll notice that the surface gets hot very quickly and the center stays cold, and that's because of this effect. However, when you hit the Curie temperature of the material, it loses its ability to become magnetized. So you'll notice this with steels. If you're into heat treating or anything like that, you heat up until it's not magnetic, and then you can quench. The Curie temperature and the transformation temperature for austenite are not necessarily related, but this is a common technique, and it shows that ferromagnetic materials heated past a certain point lose their ability to become magnetized. So when that happens, when you're induction heating, that shell of heated material passes its Curie temperature, and then you are heating that material only in the eddy current mode. So you lose one of your two modes of heating, and that outer shell from that point onward will heat a little more slowly. When that happens, the shell inside of that, it's usually about a 32nd of an inch at the frequency ranges that are generated here. So the next 32nd of an inch shell of the material along its cross-section will start heating very rapidly until it hits its Curie temperature, and so on until the center of the bar. This happens more slowly, again because of the relative lower flux density on the inside of the coil of the magnetic field lines. And it's also slightly increased by the fact that there is conduction through the material from the hot shells to the cold shells. So it's not a discrete process, like you can't actually see it, but you will see that the heat travels from the outside to the inside, and that's why. So as I said before, these heaters operate between 30 and 80 kilohertz, and induction is a lot more complicated than what I've gone over here. I've gone over the basic principles of heating. But essentially, the computer inside dictates at which frequency this coil is driven based on sort of the feedback it's getting from the material. In general, if you read a book on induction heating, you'll notice that they talk about different frequencies for different modes of heating. In general, surface heating of metals, which is what we've been talking about here, happens between 10 and 100 kilohertz. Below that, below 10 kilohertz, you get into deep heating of metals, which is used a lot in induction crucibles and furnaces and things like that for smelting material. Above those frequencies, very, very high into the megahertz range, you can actually get something that's induction heating of insulating materials, so things like wood, plastic, and glass. And this is used a lot in industry for various different applications. I won't go over too much of it here, but the basics is this. You take two flat plates, and again, you pass that high frequency current between them, and it generates an electric field between the two plates, sort of like a capacitor. So if you put an insulating material between, you do create a capacitor. That high frequency current going between the plates creates some sort of molecular agitation, sort of like the magnetic hysteresis effect that I talked about before, that heats up the material through internal friction. That's all I'll talk about for now, about that. But I want to talk a little bit more about this heater and the cooling system that I built for it, and sort of the decisions that I made in putting it on this cart, and then we'll go from there. Now I'd like to talk a little bit about this heater in particular and the things that I've done to it. This is just a regular induction heater that you can find on eBay. They're all pretty much the same. I think they all come out of the same factory. There is a brand called US Solid, which is sold out of the United States, but I'm pretty sure it's the exact same heater, and it's double the price. So go figure. This was about $500 on eBay. If you wait until a new shipment comes in, you can usually snatch them at a lower price. And this is the 240 volt version. They do sell a 120 volt version, but it's junk. Don't buy it. It's the same heater. The transformer is wired slightly differently, and EJ of the Anvil did a video of converting a 120 volt version to a 240 volt version because the 120 volt version has no power. In order to get the appropriate amount of power out of a 120 volt version, you need to draw 60 amps out of the wall, and I don't think they make circuits that big, at least in the United States. So get the 240 volt version. The only modification I really made to it out of the factory was to add these adapters for the coil. So I make my coils out of 1/4 inch tubing, and so because it's just very popular and common in the United States, and so these use 1/4 inch flare nuts. However, the machine is set up to use 8mm tubing and 8mm flare nuts, or M8 flare nuts. And those are really uncommon in the United States. The only place I know to get them is from a site called Metalworks, METTLE works.com, that sells these heaters as well. They're relatively expensive, and there's also one source for them. So I'd rather just go to any plumbing store, get 1/4 inch tubing and 1/4 inch flare nuts, and just go for it. So I stole these adapter ideas from Derek Melton, who's also on YouTube, I believe. And it's basically just a piece of 8mm tubing that came with the induction heater on a regular coil, soldered to a 1/4-inch MIP to 1/4-inch flare nipple you can buy on eBay. I made obviously 2 of them to fit this machine, and I made 2 more so that I have spares in the future. Just so that if I connect and disconnect coils a bunch of times, eventually the flares are going to wear out, so I can just swap them and go on my merry way. This machine also has some wear fittings, so there are fittings that come out of the machine itself, then wear fittings, then the 8mm flare nuts, and these wear fittings just allow you to do the same thing. Take off the flare and put it back on without wearing out the nut on the actual machine itself. The cooling system for this unit I built myself. It turned out to be cost effective. You can just use a store-bought out-of-the-box TIG cooler, or if you already have one for a TIG torch, you can just plug it in and start having fun. But it was more cost effective for me to build it, so I want to go through some of the things that I bought. All of these are pretty much the cheapest parts I could find from eBay and some tubing. So the cooling loop starts with this cheap $30 water pump. I think it's rated for about half horsepower nominally. I'm not sure if it actually puts that out. It pumps coolant up into the back of the machine and through a Y into the 2 inlet ports, through the machine internals, all the MOSFETs, and then through the work coil, back out the outlets. There are 3 outlets, and those had to be wired together. I ended up plumbing in a valve in the back that can divert the flow of the coolant in case I do want to turn this into a TIG cooler and use the system not for the induction heater but for some other purpose. Once the coolant comes out of the back of the machine, it goes through this radiator down here. This is just a cheap radiator that's typically used for a transmission cooler, so it's built for hot oil, so it can more than withstand the temperatures that are involved in this. And then it's cooled with a 12-volt, 80-watt transmission cooler fan. And that's just powered with a small 12-volt power supply that's bolted to this thing. The entire cooling system runs off of 120 volts, while the machine runs off of 240 volts. And I have a long 120-volt extension cord, so I can plug in the cooler wherever I need it and keep the heater next to the 240-volt outlet in my shop. The coolant in this is not car antifreeze. You cannot use car antifreeze. Most people use just an off-the-shelf TIG cooler fluid, but that's pretty expensive. To fill this system would be more than $100. So I decided to cut that price in half. I found this propylene glycol you can get at Tractor Supply. It's a cattle feed supplement. It's $25 a gallon, and I cut it 50-50 with distilled water, and it works great. Propylene glycol is used in vaping a whole lot. It's also used as a cattle feed supplement. This is the Aspen material. I'm sure it's just as good as any other. A 50-50 mix of this brings the freezing point of the coolant down to minus 30 Fahrenheit. So even though you can see my breath, the coolant is still liquid. So that's great. The thing that you want to avoid is car antifreeze and those other all-in-one solutions, because they have gelling agents and they have salts in them that, while they cool perfectly fine and they don't have any effect on the metals, they do conduct electricity, and that can cause a lot of galvanic corrosion between the different metals in the system. So you want to use something that's as resistive as possible. You don't want to use a conductive cooling solution. The last thing that I want to talk about is coil treatments. A lot of people will use the fiberglass wrap that comes with the coils that come from the factory with this machine, and that stuff is useless. If you go to very high heats or if you use large pieces of material, you'll end up frying that stuff. It melts at a fairly low temperature, about 1700 degrees Fahrenheit. It doesn't last very long, and it mostly just gets in the way. A good solution that I've seen, that I actually have not implemented, you can see all my coils are bare, is to use furnace cement. So a lot of people will dip their coils, let it cure, and that way a piece of metal in here will not short out against the inside of the coil and wear it out prematurely. So when I go through my bucket of furnace cement, I just have some dregs left. That's probably what I'll do to my coils, is dip them in furnace cement. It doesn't have any impact on the magnetic flux or anything like that. It does slightly decrease the inner diameter of your coil, but that's worth not having to spark out as you short across 2 sections of the coil. So now let's talk a little bit about coil design. I'm not going to go through the process of actually making a coil in front of you. This guy EJ of the Anvil has a couple of really good videos. You can also look at videos of plumbers who bend copper tubing into this. Long story short, I just pour sand into here through a funnel, crimp off both ends, and I can bend into any shape I want. Even at coils as small as this that has a 5/8 inch ID. In terms of materials, copper is just the best. It has a high electrical conductivity and a high heat conductivity. So any heat generated in the coil is wicked away very quickly by the cooling water. It also it's not ferromagnetic, so it's not going to heat up itself very much. It's just going to be heated up from the current going through it. If you have gold and you have a lot of time and money and you want to make your coils out of gold, those would technically be better, but they'd be very expensive. So we just use copper. All of my coils are made out of tubing. In industry, you sometimes see single-turn coils that are a solid piece of copper that is brazed to a piece of tubing to allow cooling water to flow through. And this can be really handy for a single-turn coil if you're making something with a very intricate profile, like a gear blank, and you want to machine the coil to match exactly the shape of the piece that you're trying to heat. However, for general-purpose heating, for blacksmiths, multi-turn coils, or even short single-turn coils in this sort of shape made out of tubing, are generally preferred because they do the cooling water circulation and the current carrying at the same time. So another type of coil that's really popular is this kind. It's called a pancake coil a lot of the time, or a flat coil. And these are a lot less efficient than the multi-turn coils because they're sort of open in nature. They don't constrain the magnetic field lines into a toroid that's going right through the center. So as such, they're calculated to be somewhere like 60 to 75% as effective as these coils, but they're great because you can heat sheet metal with them. You can pass over very thin objects, and you can control the degree of heat that you get depending on where you put it over the coil. These are pretty handy to make, but they are less efficient. Another kind of coil, one that you can see EJ the Anvil made, was a C-shaped coil. This one didn't end up working for me, but you can see the basic principle where you sort of have this C-shaped yoke, and it allows the current the magnetic field lines to travel through the yoke, and it acts sort of like an open multi-turn coil. They are less efficient because that magnetic flux isn't restrained on this side. But you can imagine that it'd be very handy for putting in a long bar, doing a forge weld if it has something fat on this end and fat on this end where it normally wouldn't be able to pass through a multi-turn coil. And this is the last type that I have. This is sort of a hairpin coil. This can be handy for inserting into a hole and heat treating the inside of a hole. That's done a lot in industry. This can also be really handy for putting a knife blade in between here. I use it a lot for draw knives. And heat treating just the edge while leaving the spine of the blade nice and soft. These are even less efficient. These and internal coils, so a very small coil that might go into a hole for something, they're even less efficient because, again, they're not concentrating the magnetic field lines inside the coil. The toroid of magnetic field lines is sort of more loosely packed on the outside of the coil. And so these are somewhere between 50 and 60% as efficient as the multi-turn coils in terms of their heating. So that's mostly it. You're only limited by your imagination. If you have a part, there is a way to heat it. You can look through old industry texts or confer with other blacksmiths. Someone has probably had your problem before and designed a coil to suit it. Lastly, there are some commercially available, again through Metalworks, wands. Basically, these connectors right here attached to the coil, but they're flexible. They're coated in rubber, and they allow you some degree of freedom. They're all well and good. I'm going to be doing probably a video at some point building my own. But they are very, very expensive, and I've heard some stories that their efficacy is sort of mixed, so take that with a grain of salt. So now I just want to talk a little bit about coil design. I see a lot of guidelines out there on the internet, but they don't seem to be necessarily informed by the actual theory of induction heating. They just sort of seem to be general guidelines. For instance, using no more than 2 feet of coil to make 2 feet of tubing to make your coil. And those aren't necessarily true. They don't have to be hard and fast rules. It all depends on what you're trying to do. There is this great book published by Frank Curtis, I think originally in 1944, called High Frequency Induction Heating. Induction heating's been around for a long time. It's a really good book, and it's published by McGraw-Hill, but I was able to find a copy for free through some library online. Take a look at it if you're interested. Most of the material in this video comes from that book. So I guess the first principle of coil design is that you want to use the smallest coil for the job at hand. The reason you want to do that is because a smaller coil basically chokes down the inner part of the toroid that I talked about before, and it concentrates those magnetic field lines in the material, and you get a faster heating rate. This is a 5/8 of an inch inner diameter coil, and it'll bring 3/8 of an inch material up to a welding heat in about 15 seconds. But anything smaller than that, you start to see a diminished heating rate. You wouldn't want to use this coil, which is about an inch on the inside, for heating 3/8 material, just because the magnetic field lines are more spread out. Another thing that's important is that you want to keep the spacing between each loop in the coil very tight, or as tight as possible. And the reason for that is because as current is going through here, it can have the chance to escape, right? Because the magnetic field lines are wrapping around the conductor. If there is another conductor loop nearby, those magnetic field lines will continue through the coil. But if it's not, they'll just start wrapping around the coil as if they were at the end of the coil. They don't know. So if you keep the coils with a gap of about half of the tubing diameter, that's the best possible. You'll have very little leakage of the magnetic field lines, and you'll have more efficient heating. That being said, it's not always feasible, and for a coil like this for general purpose heating, I can easily get material up to 17, 1800 degrees very easily with the spacing, and the spacing allows me to get a longer heat with less copper used. That being said, if you used a huge spacing, right, like 3 or 4 times the tubing diameter, you'd notice sort of a banded heat. So you'd have hot spots and cold spots right next to each other, and the hot spots would line up with where the coils are. One more important consideration is to keep these excess pieces of tubing as short as possible and as close to the coil as possible. This is actually a pretty bad spacing right here. But if you look at this, this is where the main heat is being applied. So these extra pieces of tubing, just to get the liquid back to the heater, are kept as short as possible and as close together as possible. And again, that's to prevent the leakage of magnetic flux lines around parts of the coil that aren't even used for heating. Because we're passing current through the entire coil assembly, we're generating most of the magnetic field lines inside the coil just because of how it's arranged. But you have to remember that if we're generating current this way, coming back in this way, we're generating magnetic field lines here and here as they go around these little bits. So you want to keep them ideally as short as possible. This does look like a bit of a stick out. It doesn't prevent me from getting a welding heat, so I don't plan on making it any shorter. But if you can, you want to keep any non-heating parts of the coil as short as possible, sort of to maximize your power output at the coil itself. The last thing, and probably the most important, is the ratio of the length of your coil to its inner diameter. For multi-turn coils, you want to keep it within about 4 to 1. So if you have a 1-inch inner diameter of your coil, you want to keep it with 4 inches long or shorter, if at all possible. This basically has to do with how concentrated the magnetic field lines can get inside the toroid. Once you get a 4 to 1 ratio, those magnetic field lines will have been concentrated and will be about as linear as they're ever going to get. So adding more tubing after that only increases the resistivity of the coil, and therefore you're taking power away from the induction part of the heating, and you're just heating up the coil because it's turning into a bigger and bigger resistor. For single-turn coils, and this only really applies if you're doing something like I spoke about before with a solid block of copper in a loop with a cooling tube on the outside, you want to keep those within about 1/2 of the ID. So if you have a 3-inch single-turn coil, you want to keep it less than 1.5 inches tall, and that just has to do, again, with the passage of the magnetic flux. Any more than that, you're just turning it into a big heater. So that's it. You've reached the end of the video, and I want to thank you all for watching. This is sort of a different format for me, but I wanted to make an informational video that goes equally into the technical and the practical aspects of machines like this and to induction heating. Most videos you see on YouTube are either heavily technical, where someone is only heating up an X-Acto knife on his or her bench, and they go too far into the equations, and you sort of lose the practical application of a machine like this. Or, on the other hand, there are videos that are all about the practical applications of a machine, but they don't really explain what's going on or how it works or how you can use one of these machines in your shop to do the work that you need to do. So I hope you enjoyed it. Let me know if you did, and I'll see you in the next one.